there on New Year's 2019. After that, it's just going to drift out and go further away. And like the Voyagers, it will make particle in situ measurements to understand the heliosphere. But one question is, can you do some interesting astrophysics other than heliophysics with this? And there's an old question that goes back 50 years or so or more, which can be simply characterized as how dark is space in the optical? And of course, discovery of the microwave background was the first time we've seen an electromagnetic spectrum filling space was just 10 years earlier in the 60s. This was advanced originally before Space Telescope as a way of essaying the total population of distant galaxies. And we now have exquisite counts of galaxies with HST and now JWST, so we don't need that anymore. But the question stands, is galaxies and everything you see all there is, or is there something more? So this question still stands. What is the total intensity of optical light that we're getting from the distant universe? Can this be explained by things you know? Or if not, what is interesting? Is it something trivial like incomplete galaxy counts? Perhaps there's ejected stars, diffuse halos, low surface brightness galaxies that are not in your catalog, something interesting. And then you can go into more exotic things. There's something making light which you simply don't understand. And I'm not going to advocate anything like that. But the question is, you should be able to, if you think you know how much light everything's producing, you should be able to measure it directly. And I don't believe in murder mysteries and talk, so I'm going to give you the answer, and then we're going to work back towards this. And since funny units, which I'll explain, we have measured a solid, a high significant, at least statistically so, measurement of the background level. And that's in these units of nanowatts per meter square per steradian. And the answer is 11 of those. And we think that 8 of those can be accounted for by sources that we know about, galaxies, AGN, what have you. And the difference is not significant. And so the simplest hypothesis is that the optical background is simply galaxies. And this is something that we've tried to get to for 5 decades. So the first thing I want to do is explain what these units are. And so I'm going to go from arcane units of nanowatts per meter square per steradian to something a little bit more obscure. And that is a quantity of life called 1 fridge. And so if this is my refrigerator in my kitchen in Tucson, and there's about a 25-watt light bulb lighting this up in the middle of the night as I'm going in there looking for leftovers. So we all know how bright a fridge is. And if I put the fridge a kilometer away and open that door, and I measure the intensity of light I'm receiving, that is 8 nanowatts per square meter per steradian. And so if you might imagine living in this house out in the country, and unfortunately it's a little too bright here, you can't see the lake in this projection, turn off the lights, and then across the lake, there's your neighbors a kilometer away, and they raid their refrigerator in the middle of the night, and you notice the light. That is 1 fridge worth of light. It's actually a metric unit. Still 25 watts from a kilometer is still a metric, so we're still good. Another interesting thing for you astronomers who know your stars, I don't know, you're lucky if you don't have to get up in the middle of the night, Sheree, I'm just saying. But old guys usually do. But another equivalent unit is Sirius. And you should all know your stars. There's Orion, there's Sirius. And Sirius, the intensity received from Sirius, is actually about the same. So I just say that because I think nanowatts per square meter per steradian is a bit obscure. So let's talk about what has been done before and why we are doing this measurement. So let's frame the hypothesis that the optical background is entirely due to the galaxies, and this is where I'm working towards. And this is what you get from galaxy counts. There's counts there from Simon Driver et al. 2016, Saldina Lopez, a more recent paper, and they agree extremely well. And this is their their central value with 1 sigma error bars. We have done this ourselves with much the same source material. And if you sit down and you take the catalogs that are available, you're going to get pretty much the same thing. This is not particularly controversial. So this is what we start with. Now, there's another method which is, to me, absolutely fascinating. The propagation of very high energy gamma rays, and very high energy gamma rays is a technical term. It's energies of about a little bit under a tera electron volt. So these are quite high energy. They interact with photons in the optical background and are converted to positron-electron pairs. And so if you look at the spectrum and the gamma rays of a blazar at cosmological distances, and you look at them at different distances, you can actually see extinction occurring in the spectra of these objects. And so it says that the gamma rays along the way are being extincted, and the extinction is being turned into positron-electron pairs. And so that is testifying indirectly about the sea of optical photons on the line of sight. And so let's bring these in. Okay, and yeah, my apologies. This is, the contrast as compared to, you can come up and look at my screen if you want. So you can barely see the shaded things here. If you assume that the spectral energy distribution of light, thank you, that might help a little bit. If you assume the spectral energy distribution of light is exactly the same as the galaxies, you get this beautiful concordance. So extinction of gamma rays gives you something like what the galaxies see. Now you can see this diffuse shading up here. If you let go of the assumption of what the SED must be like, and you say, let's make it arbitrary, you lose precision quite severely. And so you're allowed to be something up to perhaps 3 times the intensity of galaxies. So let's just do what's obvious and say, okay, well, look, if there's light coming from the universe, I better be able to measure it. And that's this here. And these are, with one exception, the results previous to New Horizons. So the red points are the work of Rebecca Bernstein done with the Hubble Space Telescope, with the actual points are off the scale. This is the infrared cyber rocket experiment, which produces the purple points over here. These are reflected light from bright clouds, extragalactic clouds. Pioneer tried this itself. Zemkov was an upper limit derived by a small set of images from New Horizons in the archive, but a very small set. And the answer is these really don't tell you very much. Very few of these are significant at even 2 sigma. And even saying that there is an optical background, let alone testing the hypothesis that galaxies are something else, it's very difficult. And the reason for this is because of zodiacal light. We, as far as the optical background concerned, are living in the center of the city. We've got all the lights on, and that is the sunlight lighting up interplanetary dust. And that's zodiacal light, which you can see. Actually, the first time I saw it was on Palomar in the fall, and it's quite gorgeous to see, but it's very difficult to see through. So the sunlight being scattered around in the inner solar system by dust is a strong barrier to actually looking for the optical background. And so if you take the expected background, zodiacal light, even over at the poles, okay, the ecliptic poles, is still an order of magnitude larger than the signal. So you have to have exquisitely good subtraction of it to see anything. So all New Horizons does, and it's just simple, it's just far away. And we go out to the outer solar system and we know from measurements in situ of dust particle densities and so on and so forth that there really isn't that much out there. And so New Horizons, just by virtue of where it is, at least gets rid of this component which has confounded all measurements made in the inner solar system. So I'm going to start by showing the New Horizons team. I am in that picture somewhere if you can pick me out. So I joined the team a decade ago, actually just to help out with signal process or image processing. I didn't have this project in mind when I joined the team. And this is the group that explored Pluto, and this is right after the Pluto encounter by a month or so. And all I can say is that this is the best team that I have ever worked with over my long career. It is remarkable how well the people work together, put in to make New Horizons effective. Alan Stern is the PI there in the middle. Alice Bowman, who is standing to his right or left in this picture, is the chief engineer for New Horizons, and she's the equivalent of Scotty and saved the mission from a really near disaster shortly before the Pluto encounter. And Hal Weaver, the project scientist then, and Glenn Fountain, the project manager. And this is the science team. This is the spacecraft shortly before its launch in 2006 at Cape Canaveral. The camera that I am going to use, or that we use for this measurement, I should say I skipped over the title slide. I should mention before I go further that this research you're seeing is a product of the New Horizons science team. I was a lead for this. Mark Postman is the co-lead for this, and we worked equally on this. And so I do want to give credit. There were a lot of people, especially Mark, that put in an awful lot of effort into this project. So the LORRI instrument, which I will talk about a little more in just the next slide, is covered up at this point. It's behind, you can sort of see a circular aperture in the mylar there, which is went after launch and after a little safety check was opened up, and it's a open once only thing, so it will fail open. This is looking into LORRI, and that's Long Range Reconnaissance Imager is what it stands for. And it's just an 8-inch Ritchie-Chrétien reflecting telescope. You can see the primary there reflecting the wall opposite New Horizons. And there's a secondary, it's a Cassegrain, and you can see a secondary with a little instrumentation on it, and then there's a little stovepipe where it goes in. This opens up, it's not closed, and there is optical baffling, which ironically you can't see in this picture. I don't think you can see it. I can see it, and the fact that I can see it on my screen means it's not perfect, and it's something we have to account for. So this is the basic parameters. There's nothing exotic about this except the construction of a camera that has to survive the cold in the outer solar system. 20.8 centimeters. Probably there are people in this room that have a bigger telescope than that at home. Mine is, I have a 10-inch reflector at my home myself. A 1K by 1K CCD, also small. The field of view is interesting. That's 17.4 arc minutes. As we use it, we bin this to get the faintest images detections possible in a 4x4 binning mode. So the images we get are 4x4. The pixel scale is 4 arc seconds. The bandpass is white light. This is a no-frills camera. It doesn't even have a shutter. For each of the fields, which I'm going to talk about, we take 16 exposures, and the longest that we can expose is 65 seconds. Our photometric limit is a spectacular 19.9 in the V band, and that's a 5 sigma limit. And this is the bandpass, which just shows what I just said. This is a white light imager, and the response here is set entirely by the CCD. So this measurement is tricky, and I'm going to go through some of the things that we had to think about. The first question that we asked is, is New Horizon a good platform to measure the background? We're in daylight, even 57 AU out, which is where we made these measurements. Okay, the sun is still extremely bright. And so we did some ray tracing to make sure that the LORRI aperture was not receiving scattered light from the spacecraft. This is a CAD-CAM model. You see the LORRI aperture at the left. There's the fixed head star trackers on the right, which orient the attitude of the spacecraft. And for our original observations, this was our first paper where we used purely archival observations. We projected sunlight onto the spacecraft from the appropriate geometry and measured how much light was getting into the LORRI aperture, perhaps bouncing off of things there, and it turns out that this was negligible. We went through an exhaustive set of things. So this is the first thing we tested was the spacecraft shadow was acceptable. We were concerned New Horizons is positioned by hydrazine thrusters, and if you have a little water in the hydrazine, which you always do, it might make ice crystals. This might make a little cloud of crystals out around New Horizon, which will reflect light in. This was not a concern. But we thought about this quite a bit. We verified the dark current without a shutter, which is a little bit of trickery, which I can describe to anybody who's interested, but it was possible to do that. Accuracy of the A to D conversion in the electronics, we also looked at. And this is something which gave me a headache that lasted a couple months to run this down. In front of the CCD, suspended just a few centimeters away from it, is a set of field flattening lenses made, fortunately, of fused silica, and fortunately is for what I'm going to describe. And we were very concerned with gamma rays coming off the radioactive thermal generator. This New Horizons is powered by plutonium, the decay of plutonium-38, with the heat turned into electricity. And 238 itself is an alpha emitter. That's where the energy comes from. But it's not pure plutonium-238. There are other isotopes in there, and there are daughter products. Some of them give off high-energy gamma rays. The flux is significant. And if you're holding up a piece of glass and you're sending gamma rays through it, you worry about Cherenkov radiation. And after running down the spectrum of the RTG, its state of decay, its frequency of daughter products, and more tellingly, the geometry, which is what really saved us, the fact that the RTG is essentially off of the camera and Cherenkov radiation is directional, that this was not a factor. We were also concerned about fluorescence by related mechanism. And the last one, which I asked this, and I have to put this in here, I was concerned that, New Horizons was bedecked with navigation lights, which are winking on and off, and asked that in a telecon with the PI and chief engineer present, and they assured me that they did not put navigation lights on New Horizons. Yeah, those we also talked about. We were concerned also with neutrons from the RTGs as well. Yeah, those are way, way down. So, and we have a big appendix in our 2022 paper that goes into all this in great detail. But yes, we did think of that. And one of the things that's very nice is that fused silica is very pure. Part of this, one of my concerns was also to find out the coatings on the lens, if those were nastier than the fused silica. So we tried to go through everything that might, generate Cherenkov radiation or fluorescence. The one thing we do have to contend with, and this is something that I could do without, is that the large angle scattering within the LORRI camera is appreciable. And here's a PSF, which of the sorts that you probably haven't seen before, going all the way from the diffraction scale to 90 degrees. And as you can see there, there's what I have, some 14 orders of magnitude. So the inner part is determined by laboratory experiments. The second part, and that's the dashed line, is the LORRI field of view. The outer part is from bright stars and actually sunlight. New Horizons has looked over its mission for calibration sources, and so we can measure the sky background as a function of distance, angular distance from the sun. And of course, a bright star will do exactly that. Well, any star will do the same thing. So we have to know about what stars are around our field. So here's the details of the survey. We did this at 57 AU from the sun. We optimized field selection to stay away from bright stars. The other component that comes in, which I'll talk about a bit, is diffuse galactic light, light from our starlight scattered by dust from our galaxy. That is our dominant source of astrophysical foreground, which we have to take care of. We attempted to put the fields as far as we could over the full sky, but that's very restrictive, as I'll show in a bit. And we are curious, we're interested in being able to figure out exactly what we expected for DGL. And so we developed a self-calibrated estimator that's based on our own observations. Michael Zemkoff in his paper suggested that, and his thesis student, Teresa Simmons, in her thesis, demonstrated the utility of that, and we followed that line of calibration. And there's some other things, and I won't talk further about the image processing, but again, these are questions you can ask. The field section was a little challenging. In some perverse sense, it's why it was on New Horizons in the first place. Coming out of the sun, you're going to the outer solar system, so you got the sun at your back, but right in front of you, where Pluto was for the mission, or for the encounter, it's right in the bulge of the galaxy. So, you've got the sun behind you, a bright galaxy right in front of you, and so that doesn't leave a lot of room to observe. You want to stay at least 95 degrees away from the sun just to keep sunlight out of the LORRI aperture. So this is what this looks like. So we start with the IRIS, not IRAS, it's based on IRAS, but the IRIS reduction, which is done over an IPAC of the 100 micron sky. This is galactic coordinates, of course, and this is obvious what's going on. Our first thing is we want to stay away from the plane of the galaxy. We don't want bright stars, or any stars if we can. Let's put in the sun avoidance angle, and we're left with a couple caps. Sort of, but not exactly at the North Galactic and South Galactic poles. And then we add another constraint. We're going to use far infrared to gauge the amount of dust present in the field, and from that infer what the scattered light off the dust is. And so we're going to depend on Planck observations to do this. Unfortunately, or fortunately, however you want to say, it's an odd word to use, but these measurements were made in the inner solar system and had to be corrected for far infrared zodiacal light emission. And we were a little goosey about getting too close to the ecliptic, so we also excluded that because we weren't sure if that strong correction was completely accurate. So given that the places which are not colored out are where we can observe. We also did some calibration fields. And this shows we selected some, 60,000 trials over the full sky that was left to us to see what we would find. And our constraints are scattered light vertically, an estimate of diffuse galactic light horizontally. And the fields we selected for our present survey that I'm talking about, that Mark Postman et al., our paper just came out last summer, those are the green points where he had minimized the expected effects of diffuse galactic light and scattered starlight. The red points are fields, except for this one here, fields we did with our initial archival study, which was published in 2021. The symbol over here was a test field for this that we did in 2022. What the yellow points are our calibration sequence. Here we've held down the scattered starlight, but we have now gone over a range of fields where we expect strong contributions from scattered galaxy light. And so that's one of our calibration sequences, and they will be used with the regular green fields. And then we have likewise the same thing where small dust, but strong scattered starlight to help calibrate that as well. So this program included calibration. Okay, so this is what we're left with. There's our field with the fields that we've selected for science. And then skipping over the image processing, we had 16 fields to work with, and this is what we got. And there we have returned to our designation of intensity in nanowatts per square meter per steradian. And you remember that galaxies are expected to contribute 8 nanowatts, and so we're not anywhere close to that. And gosh, look, there's an awful lot of dispersion among the fields, at least to the right. And these are our field designations, all 16 of them, organized in increasing total light. So this is simply the raw total light. After you get rid of all bright stars in the field, you get rid of cosmic rays. And this is critically, because there's a little sleight of hand here, we also exclude bright galaxies. Now, they are part of the integrated galaxy light integral later on, but for our first measurements, we are leaving them out. And this is what we get. And so we know, however, that there are gobs of astrophysical foregrounds present in our field, and we have to account for them. Integrated starlight, these are faint stars below our photometric detection limit. We know that there are galaxies below that, and we are going to include those in an integral, but we need to understand what the expected level is. Diffuse galactic light, I've talked about. There's a little bit of H alpha emission over the full sky, which will also fall in our bandpass, so we account for that. Scattered starlight, and as I said, we initially exclude bright galaxies that we can see directly. This is a quick slide that talks about our galaxy and starlight background. We use existing galaxy counts in multiband. We take account of the chromaticity of the galaxy counts as a function of apparent magnitude. We integrate over the full passband, and these are technical details, but we tried to be careful. And the histograms on the right, these are our 16 science fields plus our 16 calibration fields. And that shows the dispersion of integrated starlight in the blue and integrated galaxy light in red. And that variation there is entirely due to bright galaxies in the foreground. We cannot see the faint galaxies directly, so we have to assume a uniform intensity of galaxies over the whole sky. But of course, there is cosmic variance from field to field, so that will show up as an error term in our calculations and our estimates. The diffuse galactic light was a challenging problem. And so what we're basically doing here is we want to know how much dust is in our beams in each of the fields. And so we assume that far infrared radiation as provided by the high resolution imager on Planck is going to tell us what the mass of dust is. It is one thing to know what the mass is. We have to know what that particular mass scatters, and that's the calibration sequence. So given scattered light as a function of dust mass, it's really some sense like an extinction curve, and that's what we do. Originally, we were going to use 100 microns to estimate the mass of dust present. But we found out, that 100 microns, it's on the Wien side of the black body curve, and so it is sensitive to temperature of the dust. The dust is typically 20 degrees Kelvin that we're looking at, but that's plus or minus, a handful of degrees. And that will make variation itself. So we have to account for differences in temperature of the dust from field to field. And after a little bit of exploration, we went to 350 and 550 microns, which are on the Gene side. And there you can see these graphs show variation as a function of temperature normalized at one value. And at, I think it was 18 degrees, yeah, it's 18 degrees. And you can see that, we're much more sensitive to the temperature at 100 microns than we are further on the infrared. And if we look at our, and one thing we also have to do in this game is to account for the actual cosmic infrared background as part of the work. So the way our estimates of DGL works is we take out everything that we know about, and those were those sources that I discussed, the integrated galaxy light, starlight, scattered starlight in the LORRI camera, bright galaxies, H-alpha. We take all of that out. We claim what's left is DGL, and it's called DGL plus. It's DGL plus stuff we didn't know about. And some of the infrared flux, and in fact, about half of it in the Planck bands are from the cosmic infrared background, which for this exercise, we're not interested in doing science with. It is an annoyance that we have to correct for. And so we use some estimates provided by Odegaard on what this is. And this shows how this works. If we simply plot far infrared flux in a band, and these are not our fields, but just points that we cocked up to illustrate it. And there, if I regress that with infrared flux, and there's zero DGL, actually the intercept getting rid of the setting the infrared flux to zero gives you a negative intercept, so negative brightness in the field. That's not very good. But if we take out the cosmic background in the infrared, okay, that moves the whole flux scale over, and there we get a positive intercept. And that 0 point is effectively flux that is not explained by any sources we know about. That's what's left over after we have accounted for everything. And so we do require knowledge of that. As I said, this is provided by work by Odegaard using Planck observations. And so we work in two bands, and we use, this is work done by the Planck collaboration, we use their estimate of galaxies in the field in the far infrared using their generalized needlet method. And that tells us what to take out for galaxies. Odegaard regresses what's left behind with H1 and produces a monopole value, and those are what we use for the infrared background. Now, I did run into some concern that, Planck is not particularly well calibrated for absolute measurements, but since we are using Planck infrared measurements for our dust measures, these, null each other out. So we're not, the absolute thing may be bobble up and down a bit, but the difference across the fields and the background itself is tied to the same calibration. And so here's what these relationships look like in individual bands. This is our total sky with everything taken out that we know about, leaving the DGL behind at 100 microns, 350, 550, and we went and we looked even at 850 microns. And you can see that the scatter is best there at 550 and 350. We didn't want to do a monochromatic band. We wanted to use both 350 and 550 together, and that has effectively a color or a temperature term in it to account for the difference in temperature between the fields. And this is what we went with, and there is our error that we have in the end. Now I'm going to explain how we get the actual optical background flux. So keep this measurement in mind. And now we're going to go through this again. So there are our total sky values that we had. And now I'm going to show what we get for the foregrounds in all these fields. And so there, the blue is the inner-rated galaxies that we can't see below our photometric limit. The narrow little red line there, that's H alpha in our field. The green are faint stars that we can't account for. We use the trilegal package to estimate what is there. And the yellow is the unfortunate scattered starlight that we have to correct for, that Laurie incurs. We do this with 3 catalogs. We use the Gaia catalog, the Hipparcos catalog, which is called the Tycho catalog. We even use the Yale Bright Star catalog, and we integrate out to some 40 degrees with that PSF that I showed earlier to account for all scattered light in the field. And the error bars on top of the yellow, that is the error for each field in the decomposition. And then there's our total sky measurement with the error associated with the Ross sky. And you see that all of them are a little bit above the decomposition. This does not, however, necessarily mean that there is a true signal. In this game, systematic errors rule the realm. And so one simply doesn't take different fields and add them together and divide square root of n. One has to do an analysis that encompasses both systematic and random errors. And did I skip over? I skipped over a bunch of slides, so that was a good trick. Okay. So we use a Monte Carlo process. We have a ledger sheet for all of our random errors in each field. These are random errors in each component, and each component that we talked about has both random and systematic components. So we start with our total sky, we start with the measurements of each foreground component in each field, and we roll the dice for each field for the random component, and we roll it for the whole sample for the systematic error components, and we do this some 10,000 times. One little trick there is that we did a self-calibration of the DGL estimator from our own data, okay? And so there are errors associated with our observations to do that in its own right. And so if we change any of the observations we have, we also change the calculated relationship. So I showed you an example relationship in the one slide. We don't actually use that. And each trial, we go back and recompute our DGL calibration. So that is included as part of the Monte Carlo analysis, okay, to make sure that we're also accounting for the fact that all the errors in our total sky also influence our estimate of DGL correctly. This is what we get. There are two figures here. So now this is putting back in the bright galaxies to account for the total. And there's very little error associated with that because we can identify and photometer the galaxies. And so on the left is the total signal of the cosmic optical background, and that is 11 nanowatts per meter square per steradian, or 1.5 fridges about. And the shaded line there is what the IGL produces. And that, the difference is, as we say, not significant. And then there's the individual fields. And the difference is explored further here. We take out the integrated galaxy light, and there's errors associated with it, mainly because of cosmic variance and uncertainty, both in extrapolation and in the validity of the counts themselves. And that is our anomalous signal, the stuff that we can't explain. And the anomalous signal is, essentially 3 nanowatts plus or minus 2. So it is an allowance for things that you don't know, but it's hard to argue that there is something significant there. And so I go back to what we had early on in the talk, which are our direct measures. And so now we have added points from New Horizons that were not there before. And there are a variety of measurements there. You see NH21, that's work that I led the team with on purely archival observations before we ran the survey that we just talked about. And there we got a high value, but with large error bars. Our trial of one field in NH22, which you see is very weak and you can barely see that, and there's a reason for that. We found out that we had made a mistake and a correction that we applied to the infrared fluxes on that. And I am happy to talk about that. We published that result as an anomalously bright background, and we are saying no, that we are superseding that. We have found out why that point is high, and when we correct for our mistake, and that's NH22 revise, the error bars go up, but the value goes down. The black are the points that we have determined from our current survey, which float above the galaxy counts a bit, but not significantly so. The other point, Teresa Simmons, I don't know if she's here today, but she, I believe, is working at IPAC, and she did thesis work using archival observations of New Horizons, not the ones that we're talking about today, and got a very high result, and I'm happy to talk about that in questions. In the meantime, the very high energy gamma ray people have been busy as well, and I'm going to zoom into the region where we have our results. And this is work done by Greux, if I said that correctly, et al. That just came out a couple of months ago. And there they were able to relax the assumption that gamma rays have an SAD, or that the optical background has an arbitrary SAD, but in a sophisticated way that allowed them to get precision, even assuming an arbitrary SAD. And that's STEVE-CAT, and that again is dead on the galaxy counts. And so this is a summary of what we've done. In their case, it is a value at that particular wavelength. So that's how we presented. We wanted to put it at our pivot point. They have points at other frequency or other optical wavelengths, and they can do this in their analysis, okay? And we didn't put them up on this thing because we just wanted to have the direct comparison with New Horizons. So what do we have to show? We claim that we have a solid, high significant detection of the optical background, and that's our 11 nanowatts. When we look at the difference, we do not find this significant. And does this mean something or not? Simon Driver allows that there might be 20% more light not accounted for in the HST galaxy counts, perhaps tidal features not in the aperture, low surface brightness galaxies. And I think this is a very interesting question. I had a long conversation with Phil Hopkins about this this morning. It's not particularly well known how much light galaxy formation throws out of the galaxy, so that's an open question. But there are results, and there's two results. Our simplest and most obvious interpretation is that the optical background is completely due to galaxies, and no additional or exotic sources of light are needed. And the thing which is fun is after all of this work, for the first time, we have the three measurements all agreeing with galaxy counts, high energy, very high energy gamma rays, and direct detection now converge at an interesting level on consistent values. And I don't want to touch this further, so I'm going to stop.
Yeah. So the continuous curves in line, violet or some deep blue, are they the gamma ray?
The lines are galaxies. The bands, the colored bands, are the very high energy gamma rays.
Gamma data does just have for shorter wavelengths. The background is confusing.
I'm sorry, say again, Tree.
So if I just look at the gamma ray data, it's got a shorter wavelength below your slow wave.
Yes.
The sky is getting darker.
Yeah, I mean, that's what it says, sure. Yeah. Yes, I understand. Yes. Yeah. It's a good question.
How much of the total background from the galaxies that you saw brighter than 19.9, and how much is the 20?
Yeah, it's a minority, but a large minority. I should just bring up the slide, but it's about, I think, 40, 30% or so. Yeah.
Fitting for the extragalactic infrared background, 350 microns, subtract, it seemed like it was actually a sign of the intercept.
Yes, it was. Yes.
About how Planck actually attempted to determine that. So you use the value from Planck.
Yeah, so we use the value from Planck, and we depend on the kindness of others to determine the cosmic infrared background. And so the regression on this is to use two measures. One is far infrared light in your beam, and then H1 intensity in your beam. H1 and dust travel together. Okay, and when you do that, you find yes, yea, verily, there is a correlation. Okay, and you regress that to 0H1, and that intercept gives you the cosmic infrared background. You presume when there's no H1 that there's no dust there, and that's where that value comes from. So that is an assumption, but that's where we get it from. Well, the relationship is not perfect, and actually, when you get to significant dust column densities, it's also nonlinear. So, we looked at Odegaard was interesting because he did this with, very weak dust and very weak H1. I don't know if that answers it, and I don't know enough about the technical details of how he picked his data points. Where you got a beam from Planck, and you've got H1, which was presumably higher resolution, so you could probably degrade it. But to be honest, I don't know how that was done in detail. Yeah, that is correct. That is correct.
I would guess that number is very dependent on whether you're looking in the direction of a massive galaxy cluster versus a random point thing. So I don't, I mean.
Well, no, I wouldn't say that. This is the galaxy counts, okay, which are, done with HST, and you know all the surveys that have done that. There will be an error associated with how well you know that, and that is there will be some cosmic variance. But those are wide area counts, at least as wide as you can do with Space Telescope, and so they shouldn't have galaxy clusters in them. So we take that as the cosmological density of, or cosmological intensity of integrated galaxy light. As for our LORRI fields, okay, um, you know, I can say that there were no obvious galaxy clusters in our field, and there's 17 arc minutes across, and so, cosmologically distant clusters are going to be smaller than that, so I don't think that would bother us that much. But yes, I mean, it would be something to think about. I mean, being able to only go down to 19 or 20th magnitude, there's a concern. Something we might be able to do. Roman flies, we can go back and potentially revisit this and really turn down at least that source of errors. It's not going to help us tremendously because integrated galaxy light is the third most prominent error. So we'll do a little better, but not markedly better if we have better information on that.
Now, Verge, do you think another direct detection experiment is justified?
No. Leave it alone. No, I think this will always be interesting. I mean, LORRI was absolutely not designed for this. I mean, first of all, the most obvious thing is that, we don't have any chromatic information. And so you'd really like to get that. Okay. So you want that. Sorry? Yeah, I mean, one of the things which really irritate you can't see this, but with the picture I had when you see that, you can see the baffles, and you shouldn't be able to see the baffles, but you can see the baffles because they're scattering light. And I asked Hal Weaver, said, why couldn't you just glop this up with Vanta Black, and I don't know if people are using that or not. This promises to be really good stuff, but absolutely, we'd like to have a camera. No, you can do better. I have a close friend of mine who's a physicist who looked at what we were doing. This camera is designed to image Pluto, and his words to me reading all this stuff is that I was abusing the camera. I mean, it wasn't designed for this. And so with a sensibly designed camera, you should be able to do a lot better. A bigger telescope, so you go fainter, would be better. Spherex is going to try this. This is from the Earth environment, so they're going to have to work very carefully. And I can't say they understand exactly how, the line intensity mapping works. Their claim is that they will be able to get around ZODI, so they will be able to test this, and it will be interesting to see what it is. But no, I think this is the first time we've been able to do this. I think it may, in fact, be interesting to do a lot more of it. But I checked the train schedule, and nobody's going out Pluto way for a while, so you may have to be patient.
What about the ecliptic?
Well, we try to get above the ecliptic as well. Yeah, Pluto. Oh, you mean with the spacecraft? Oh, sure. I mean, that would be interesting. I mean, one thing you could do is just go in the opposite hemisphere so you don't have the galaxy hanging out in front of, put the bulge behind the sun. You're going to have a cleaner area to look at. So, that again, you get what you get and you don't throw a fit. But yeah, one could absolutely do some better things. Whatever is in the galaxy count. I mean, or yes, I don't know. I mean, AGNs are in galaxies. Okay. Yeah, the answer is, George, I don't really know. I assume, if you look at galaxies, I mean, the question is, are there faint AGN that you see? If they're standalone AGN like faint QSOs and they're not in drivers counts, then that's an interesting question that I haven't thought about. Yeah. So, okay.
I'm a little confused by the fact that you associate the dust with H1. That just H1 is the gas, or what about the molecular gas?
So I should know the answer because I read this and I don't. I'm trying to remember what Odegaard said about that. He discussed that, and I believe the answer, and this may be completely wrong, but I'll say it anyway. He worked at very low dust and H1 column densities, so I don't think there was much molecular hydrogen associated with that. No, no, absolutely no, no. Oh no, oh no, no. So the DGL is only stuff in our own galaxy. Okay, whatever the background galaxies does, that's their own business, and we'll let them at it. But no, no, that's not in there.
Right, I probably should know this, but I was confused about the fridge. So the fridge is, and you said it's also as bright as Sirius. So these are
Yeah.
sources. So you're saying if you spread them out over the whole sky or over a steradian or over what area?
Yeah, I need a drink before I can talk about intensity and surface brightness. And yeah, I was taught this stuff my junior year by Peter Goldreich, and it was sort of mystifying then, and it always comes up and you get gummed up in it. What we intend by saying that is received light. That is, hold a card up, okay, or hold your hand up. What is the received flux on that card? And so Sirius, of course, is a point source. It's not Sirius all over the sky. If you stand out, and are able to block out Sirius, so you're in a Sirius shadow. In fact, you could do this, right? Make a little thing to pick out Sirius and put your hand behind it. That difference, okay, and how much light you're getting from Sirius, should be exactly what we're trying to describe. And the fridge is the same way. You're up, except for Shri, who doesn't wake up at night. Yeah, yeah. What do you look at? No, well, you see, but the neighbors are bothering. You're not looking at. You've got your windows open and your wall lights up because they open up their refrigerator. That's what you're looking at. So no, that's the same. That's the same thing. Okay.